there is just too much material. In 1 hour, I can't tell you that the whole world got it wrong and prove it to you, but I'll try my best, okay?
Can you share your slides with us?
Yes, they're with IEEE, and they're free to upload it or do whatever they like with it.
Oh, okay.
So I've given a copy. They have it. And Mike and whoever are free to share it with everybody, because you want to look at it later and see what I did. This is very complicated, I'll tell you that. I thought switching power electronics was difficult. Resonant power is extremely tricky. Okay, so I'll get started if you don't mind. Thanks for showing up, and thanks for inviting me to Mike and all the other guys. I was supposed to come in last month, and then it was in my spam folder, believe it or not. And in my spam folder, there was also the whole trip for China tour, which was 6 cities and all that. I missed that too, and they were like, what the hell is going on with this guy? So I missed that one also, China tour. So you might know I went in 2016 all over China, 5 or 6, 7 cities, I don't know. And they were repeating that, and I missed that too. So thanks to spam folder of all the. So anyway, so let's get started here. The title is too long, I know. Title, Scaling Laws to, I don't know what I was smoking when I wrote that title, but you'll get an idea about that. All right, so just to start off the conversation, I'm telling you my position, all right? We want the industry to move forward. Everybody wants that, right? So I'm going to share a lot of information with you today, in trust, okay? It is designed to help you find alternate solutions. I'll tell you the problems. You're free to go and find alternate solutions. If you find our solution, then we'll be happy to work with you because it's proprietary. All the material presented today is very well protected by White & Case, dating back from 2016. And we do that as a company, so you'll have to forgive me for that. We would love to share it. All my books are available. They have a lot of information. I hardly make any money out of those. I made more money at National Semi writing in EDN and all than I ever did in my books. So just keep that in mind, and I'm very happy to share it with you. Success is the meal best, which tastes best when it's shared with people. So you go to a party, and so we can celebrate a success here. And another position we have in our company is to be very true to the facts. Unfortunately, right now, it's a joke. Believe me, I know it. I know everybody what they're bluffing, what they're lying. We don't have any patience for that. So I will be sticking to the facts. If you look at any of my videos, they're always uncut videos. I don't edit my videos. They might look sloppy to you, but that's the reason I don't do it, because people put in things and they mix up things and they try to trick you. That's not what we do. We are extremely thorough in our whatever we've done. We've done MathCAD, we've done simulation. I'll share some of them with you. And we will say it the way we think it is. So don't shoot the messenger. I'll tell you that the entire world seems to have got it wrong, and I'll try to present that to you today. And it's come as a slow realization. When I did it, I didn't realize how far we are ahead. But as I go around to customers, I realize, my God, they are in the jungle. They don't even understand the problem. Leave aside, find a solution. Okay, so let me get started. What happened here? All right, so first of all, thanks to Michael and Sushil for inviting me here. And this happens to be hallowed ground for me because I used to work in Building D for many years, 5 years. Building E was the place where this guy used to throw computers off the roof, if you remember him. Okay, not at my time. HR had stopped him long before that happened. And there was another famous guy. He was also called Bob. And this was the culture here. Everybody was doing that. So now you understand why I'm homesick. Nobody gives me the finger anymore. Okay. So I'm back. At the end of the seminar, you can all give me the finger. All right, so back in Building D, in my own humble way, I came up with something called current ripple ratio, which you might have seen in my books. I called it R. I was walking around thinking, what should I call it? Let me keep it simple. So R, ratio, ripple, whatever. That has been a very unifying concept if you have understood the importance of that. People have started recognizing that. Now, unfortunately, all my original app notes, they changed the names and removed names, and that's not actually very conducive to authors, because if they had taken off my name, I wouldn't have been able to go to any of the publishers and say, look, I wrote that app note, please, can I publish a book? So it's nice to keep the names, and National Semi was very good at that, and rewarding you when you write. So some of the original app notes are still there, and I've given the links. They are loaded in various universities and all that. And so this is the one where I introduced, it hangs, current ripple ratio. It is the ratio, the delta I, the ramp, divided by the center value. Now, I started with the buck converter, and that was the first thing which came to me. And then I realized I can extend that concept. I did that in 1246, which is also uploaded. And this, by the way, made it as cover story of Power Electronics magazine under the title Reducing Converter Stresses or something like that. It was there as, they used to get advertisements based on that cover. So that was a very well-known thing. And these are what spiraled into my books, by the way. So I owe all my success to the culture they had at National Semi, so I'm making that very clear to you. What I did was, instead of center, I just defined a center of ramp, COR. And I basically said, for a buck, it is the load current. And for the remaining two topologies, it is the load current divided by 1 minus D. But for all the topologies, whichever way you look at it, the optimum value is about 0.4 or 0.5. And because it's a knee, and that's the point of maximum returns. After that, you're over-designing. Below that, you're under-designing. So that you'll find in this thing. I don't want to go into all that. The reason it is important is that helps me explain scaling laws to you. Because when you scale to any converter, my ripple ratio applies to any topology, any power level, any frequency. So if I scale a topology to a different frequency or different power level, if I have not maintained the same R, I'm in trouble. Then it's not an optimum topology, and I'll be fooling you if I say that that is proper scaling. So basically, all the scaling I'm going to tell you about maintains the current ripple ratio. So there's some of the scaling laws we understand intuitively. One of the things they say is, oh, let's go to higher frequencies because my components will get smaller. Now keep in mind that inductance may have nothing to do with the size of the inductor. Similarly, capacitance may not have anything to do with the size of the capacitance. So just keep that in mind. But let's see what happens. We go to higher frequencies, typically, to reduce the size of the components. So basically, I can prove to you, and I'll do it today, that if you have a converter working at 100 kilohertz and your boss says, it's well designed, it's optimum, by tomorrow night, I want you to make it 200 kilohertz, same power, same everything. What are you going to do? Are you going to sit the whole night looking at my books? No. Very simple thing you have to do is to simply take the capacitance and divide it by 2, and the inductance and divide it by 2. And in this case, the size will also remain the same, will halve, because your load current size is dependent on energy storing capability. For example, half Li square. I has remained the same because you've kept the same power level. L has become half, so the size of the inductor will get half. So if you double the frequency, you're going to halve the size of the inductance, halve the capacitance, and halve the size of both components. That's what happens. Okay, now there's a power scaling law also, which is not so obvious. This we kind of intuitively feel. Power scaling, I'll tell you. So I used to explain that in my China trip. So the Chinese environment is really, and so he says, boss comes and says, this is a converter which is working 5 volts, 1 ampere, 100 kilohertz. I want it by tomorrow, I want you to make it 5 volts, 2 amperes, 10 watts, double the power. I don't care what you do. I want it by tomorrow. What's he going to do? He's not going to read my books. So what he does is very simple. If he has to double the power, he has to double the capacitance and halve the inductance. I'll prove it to you. So if it's an optimum converter, you'll feel it in your blood very soon when I explain it to you. So just give me a little patience. Now here I'm going to double the power, keeping frequency the same. And I'll show it to you. Let me stretch, this is a buck converter just to start with. I stretch it, I make that waveform twice the size, exactly twice the size. This is a new converter. So the load current has doubled, and the delta I has doubled, right? Now you can see immediately the time was the same, blah, blah, blah. The slope has increased. Obviously, the inductance is halved. So just read the logic, and I'll move on. So you have halved the inductance to achieve that. And the current ripple ratio remained the same because delta I doubled, but so did the center. I also doubled. So R, which is the ratio of the two, remained the same. That is why it is still an optimum design converter. Okay, any questions? Pardon? I'm focusing on CCM. DCM, you can go into transitions and it can get a little more complicated, yes. I agree with you. There are some exceptions, you'll figure them out. Wherever you cross a boundary or something, believe me, you'll be in trouble. So don't cross any boundaries. You don't go from one region of operation to the other, there will be problems. So I'm keeping everything else the same, region of operation the same, blah, blah, blah. DCM, I think it needs more math. All right, so this is a very simple way, and you have figured that out. Now, what about capacitance? You have doubled the power, you kept the frequency the same, okay? Look at this ripple. This is from A to Z second edition. This is the formula for ripple in terms of R, I0, A, F. So basically, you have doubled I0, which is the load current. Ripple ratio remained the same, frequency remained the same. So you still want to keep the same output because you have not changed the input or output voltages. You still want, your guy still says, I want 50 millivolts peak to peak. To maintain the same ripple, what you have to do, you have to double your capacitance. Okay, so this is an intuitive way of looking at everything. I hope you're getting this, okay? It's a very easy thing once you feel familiar with it. The idea is, in power electronics, the idea is to understand the depth of it and try to simplify it, which I try to do in my books. The problem with resonant power is you can tend to oversimplify and you'll be in big trouble. That is more complicated than you have ever dreamt of. But I will try to simplify that too. These scaling laws apply to resonant topologies too, okay? Now, suppose back to the frequency, I'll do the frequency thing. I'm basically halving the frequency by stretching it this way. And the same logic, you'll see exactly what I said. So the rules are basically, I'm going to speed past this, these are the rules. If you're doubling the frequency, you need to halve both the capacitance and the inductance. If you want to double the power, you need to halve the inductance but double the capacitance. Okay, so I've got too many slides, so you can see this in your spare time. And yes, the break frequency and all change. So if you are going to a converter of, instead of 5 watts, 10 watts, you still want the break frequency of the Bode plot to be the same, F by 6 or F by 10 crossover of, all that remains the same because the product LC remains the same if you don't change the frequency. So basically, it completes the entire picture. So you can think about it a little bit more and you'll realize that this is really accurate. Now, the C by L ratio is a very good indication of power because, as I said, if you are increasing the power, you will increase C and reduce L. Now, reducing L doesn't mean you're reducing the size of L because the size is dependent on half Li square. If you have doubled the power, I square has quadrupled, L halved, you still have twice the size of the component. So if you double the power, yes, your L and C will be twice the size. Inductance has come down, but the size did not. So just keep that in mind. You have to get that visual picture of this. And C by L ratio is a very good indication of the power you can derive from the converter, optimally. Same thing is true for resonant topologies too. All right, so if you scale it this way, for example, I'm scaling it, doubling it on this side and doubling it on this side. You see, I can do a composite thing here. Oops. Okay. I can take, so the first, when I did it, we doubled the power and halved the frequency. So if I double the power, I halve the inductance. Then I halved the frequency. So L became half. We have doubled the power and halved the frequency. So L became, for doubling the power, it was half, and then you multiplied it by 2 because you had half the frequency, it became twice the size. Capacitance, when you double the power, you doubled it, and then the next step, when you halve the frequency, you double the size, because whenever you lower the frequency, you double the size of the components. So this quadruple and this remained unchanged. So this is a way you can mentally work out for any power level and any frequency level. This is the trick I used in my resonant converter book in switching power supply design and optimization. I applied it to switching converters. I actually ran this through several simulations to see, yeah, it is true actually. Even in resonant power, I can do that. So I started with a kernel, which was arbitrarily defined. I studied it. I knew how much load I can get out of it. And then I could scale it to any power level and any frequency level in 5 lines. And there was a big paper by Dr. Fredley saying design methodology of LLC is very complicated, and he had 20 curves there. It's a famous article. And all the points I got, I verified against his curves. They were all accurate, and I just did it in 5 lines. But I started with a kernel which I understood, any arbitrarily chosen. 10 millihenry, 10 microfarads. I studied it, plotted the curve. I said, this is how much power I could get. And then I can scale it to any power level and any frequency level by just simple math. Okay, I'll show it to you. But nothing is so obvious in wireless power transfer, for example. For example, I'll give you an example. Now, when you come to resonant topologies, wireless power transfer in particular, things become very different. They can be very tricky. So you would assume the same thing is true in resonant power. Yeah, it is. But there's a catch here. And that catch is safety, FCC issues, and all that. They can come in the way and prevent something. So I'll show you the example of that. Gary Meadows, a very senior guy at Intel, said, I recommend my company invest in Rezence standard because, simple, if I'm going to a frequency 6.78 megahertz, it's 50 times higher than 100 kilohertz, I should get very tiny components. All right, so this was the logic by which Intel invested in Rezence. And if you remember in 2016, June or July, they abandoned it and all their teams disappeared and they never explained why. Something like what happened with AirPower. They'll never tell you why. Who wants to say I made a fool of myself? But this is what happened. All right, so all the links are there. You can check them out. And this is the CEO of IDT also, virtually repeating the same thing. So at the highest levels, they were saying Rezence is going to be the future. All right. Reality. Do your due diligence, especially when you come to resonant power. This is from an earlier 2016 presentation of ChargeEd. We had not yet perfected the firmware. We had a manual version, but this was already true. I said, okay, so here is the resonance coil for 5 watts. This is the Chi coil for exact dimensions. This is our coil. Tell me, Rezence was 50 times higher in frequency. How come that they have a power density which is even worse than Chi? Do you understand? This was the failure of Rezence. They never told you why it failed. Because they realized much later in the day that FCC does not allow them to sell their product unless they achieve 6.78 megahertz plus minus 0.2% tolerance. That is plus minus 15 kilohertz. The only way you can achieve that is not by ferrites, not by commercial capacitors. You had to make a big precision PCB as your transmitter with a distributed capacitance. And so you had good user experience, yeah, because it was a huge surface and you were moving your thing around. And you couldn't have metals in the neighborhood because it would cause a frequency drift. That was the failure of Rezence. So if you look at all their evaluation board, even here, you see how they place the electronics on the side. If the electronics is underrated, it detunes itself. So this was the big problem they never told you. And the Dell Latitude 7285, they somehow hacked it in, but they did it in the wireless, in the keyboard, which is all plastic. It cannot be near metals. It detunes the thing and the 0.2% tolerance and production can't be met. You are not going to sit and manually tune every unit. So that is why Intel stepped out, and that is why Rezence failed. And anybody who comes today and tells you that they are reviving Rezence, please, there's a history behind this and a technical reason which they probably don't understand. And yes, our coils are tiny, so maybe I just give you a quick demo of that so that you realize what we are doing. This is a 12-volt power bank. You can see it, 12 volts, straight, nothing, no gimmicks. I'm going to turn it on. It's going to come on. Best foreign object detection in the world. It detects a coin without any communication. I remove it, it's gone. All right, nobody can do that. I put a vertical load. It'll do a few proprietary sweeps. It's a very complex firmware. And then it also does Qi devices right next to each other. It's backward compatible. Oh, they're switched off. If you don't draw enough current, this power bank switches off. Okay. So it gives you 10 seconds. It's looking for Qi devices. It wants to rule out Qi. Then it goes to the next stage. All right, so it can support multiple devices in this mode. You can turn it around, you can lay it flat. You can do it on the edge. The coil is very tiny here. But if you really want to see a good demo, let me reset this. It comes on in a high power mode also. which I'm going to show you right now. Okay, here we go. This should represent about, I'm going to turn it on. Okay, here we go. So this is a proprietary high power mode. I ramp it up slowly just to, it's a demo mode. So first it waits 10 seconds to rule out chi. Then it does its sweeps. This time the blue light is flickering, indicating communication. It's a one-to-one mode. So check out the amount of power I'm getting from here. It's going to go to about 80 watts. All right? Now, can somebody come here and touch the coil after I'm done? I need a guinea pig here. Can you come, please? Okay, so I'm going to give you the coil to touch, okay?
It's running at 100 kilohertz.
Yeah, it's 100 kilohertz. I don't do high frequency. You'll never pass FCC that way. Okay, touch it. It's not even warm, I'm telling you. So this is the demonstration which takes everybody by surprise. This proves that we got it right, okay? Nobody else has got this result from a 12-volt input. Chi achieves 15 watts from 19 volts. You do the scaling, we are 80 watts in a coil which is 10 times smaller, with the resistance of the coil which is 10 times lower. And you can package it in anything. You don't need a large flat surface. You don't need to press it against the battery. You don't want to kill your battery. Put it on the edge of your phone. Put it in the case. So that's what happens when I said this is our coil. It really is. It's actually better than what I'm showing you. It's tinier and delivers more power. Yeah, there was supposed to be one somewhere. Oh, okay. All right, so the problem is Rezence failed because of FCC certification issues. At a high frequency, you have EMI and SAR issues. They gave you a narrow window, 6.78, but it was 0.2% tolerance, and they couldn't meet that ever. So in WPD, you have to do a lot of due diligence to know what will work. Just getting a lab experiment working is not good enough to show that you'll have a commercial product. This is not the age of Tesla one century ago, where he could zap you with lightning and there was no FCC or UL to complain. All right, so that's what happened many years ago. So people have hyped that up a little too much. So it's far trickier than you have ever imagined. You saw the demonstration. Nobody can do that in the world today. All right, so there's no black magic there. I've not generated high voltages. I came out of 12 volts. Okay, so another hidden in plain sight. If I double the input voltage, then V square R, keep everything the same, V square R law tells you that you will quadruple the power. Okay, this is actually unknowingly Chi standard followed this. So they start with a 5 watts full bridge. They enable only a half bridge operation. They check it out in 5, then they communicate, and then they turn on the full bridge. When you turn on a full bridge, you're effectively applying twice the voltage across the resonant circuit. You should know that, because in a half bridge, basically the DC blocking capacitor is taking half the DC voltage. So then they switch to the full bridge, and technically they can get 20 watts, but then they derate it to about 15 because they're not sure what they're doing. But that's the scaling law. I applied the same scaling law to, we are saying we can do wireless electric vehicle charging better than anybody today. Yeah, we need to put a few coils together. We haven't got there. But this is a BMW 530e. And they achieved after 10 years, Vitricity was working with them. So Vitricity were the pioneers of Rezence, if you know, and then they dropped out. They completely changed. In December 2017, they fired all their teams, and there was a huge layoff. And they said, now we're doing EV charging because of the opportunity. But they failed at Rezence, and I just told you why. After 10 years, they came up with this. Only 3.2 kilowatts through 3 inches, I don't know how many centimeters that is, at 85% efficiency. If you do the math, that's about 450 watts last. So while you're sleeping, your car has become a giant heat sink, actually. How are you going to get rid of 450 watts? And only 3.5 kilowatts. So I applied a little scaling law to, I've been in Detroit recently, so I showed them this also. It's not going forward. Okay, so I said, listen, we are getting 80 watts from 15 volts. Actually, I got it from 12 volts, but I'm underplaying it. I'm a conservative engineer. I underplay it. So here I said 15. Qi achieves 15 watts from 19 volts. Apply the V square R law. The scaling factor, if you go to EV charging voltage level, is actually 380 minimum, can be 480. So from 15, I'm going to 380, it's a V square factor. They are going from 19 to 380, V square factor. This is the scaling factor to see how they can scale. If they scale, they'll reach a maximum of 6 kilowatts. I can easily go to 51 kilowatts. Right now, with my firmware today, all I need is the hardware. So, because we got it right. EV charging today is actually the same as Qi scaled up to a higher level, exactly as this. And they have made the same mistakes, which you'll be a little horrified to know. And yes, their losses, 450 watts, because normally in all Qi and wireless EV charging, the receiver coil has the maximum heat. So 80% of the losses are on the receiver side, you should know that. So for example, if your entire system efficiency is 70%, you know that out of that 30% loss, how much is in the transmitter and how much is in the receiver? It's only 4 to 5% in the transmitter because of the thicker coils. 20% is in the receiver where you can't afford it. So when you buy an Apple phone and it has Qi 7.5 watts, have you ever done the test and found that it drops to about 3 watts only? Average is 3.5 watts. It has never crossed 5 watts. There's no phone today in existence which actually achieves a wireless charging rate of more than 5 watts. Do the math. There's lab test coming out. All right, because there's a hot coil dissipating roughly 1 or 2 watts, do the math, pressed against the battery. The battery has a protection circuit. When it reaches 40, it dials back and says, reduce the power. So it comes down to 3.5 watts. It's the biggest secret which nobody has told you. There's no 15-watt standard. It never existed. That was all bluff. We can achieve it because we have a tiny coil and it's not pressed against any battery. We don't ruin your battery, and we can put it anywhere. So you just saw that demonstration. All right, so that is what I've been telling them. Now, resonance, you can try and intuitively understand. This is a book where I explained it. It's not the only book, but you can ask one question. Why resonant? Why are you even thinking of resonant circuits? So the first answer is in wireless power transfer, by using resonance, we generate a higher voltage so we can cross a greater distance. That's one of the reasons. The second reason is you actually get very high efficiency. Resonant circuits can give you much higher efficiency. Why? Because they can produce zero voltage switching and zero current switching if implemented correctly. And nobody is doing that today. Only we are doing that. Yeah, I was explaining to Karthik, we have a little bug there, but this is what we set out to do. Okay, so now, people think that the energy in the leakage is lost. It's not lost. It's fully recoverable, 100% of it. It's trapped there as half Li square. It doesn't disappear. It's not a radio frequency system where it travels into outer space. It's a near field system. So that's fully recoverable. But in the process of cycling it, no cycling process is perfect, you will lose some of it. And it's usually lost only in conduction losses, in the resistance of the coils, in the resistance of the FETs. Provided you have enabled zero voltage switching. Otherwise, you'll lose a lot in the switching, and you'll never know what happened. So make sure there's a correct region of operation if you are enabling zero voltage switching. Then the only thing you have to reduce to get 100% efficiency is to reduce all the drops across the resistance. Technically, if I have a coil of 0% resistance, I'll get 100% efficiency. So when people ask you how much efficiency you get out of it, it's a lame question. You stop it where it makes economic sense. That's all. I'm not going to parallel 10 FETs. At some point, you'll say, well, I'm OK with 70, 80. We can achieve that. So efficiency is another buzzword which has been misused a lot. OK, so, but there is in all resonant circuits, there's a residual energy, which is called the magnetization component, which is basically exciting the transformer. And that's not been communicated to the outside. So you have to recover that. It cycles back into the supply, and then you bring it out again. So as I said, in that cycling process, some is lost. But it's all conduction losses. There's no switching loss if you do it right. And then how you control it, a lot depends on are you in the right region of operation, for example. Are you enabling zero voltage switching? Do you understand the control loop, how it's working? So I'll come to that. And then people said, oh, in switching power, we have been doing fixed frequency operation. Let's do that here. It'll reduce EMI. Okay, you want to reduce EMI, but do you realize that this is a resonant system where the resonant peak is changing all the time? That's nature. You adapt to it, you don't defy it. When you do fixed frequency switching in resonant systems, you have killed everything. Because at some point, you are switching at 80 kilohertz. What if the peak moves from this side to this side? You will go from a capacitive side to an inductive side. There'll be no zero voltage switching. You will destroy yourself. And this is what's happening in EV charging. EV charging, everybody out there has a wrong theory. They are fixing it at 82 kilohertz or fixing it at 85 kilohertz. Apple tried to fix it at 127.7 kilohertz. Biggest mistake. That's why I had predicted 2 years ago AirPower will never happen. People thought I'm just against Apple or something. No. When you listen to your friends, they're telling you where you're going to go wrong. And you pay the price for it if you don't listen. They did, okay? The peak actually moves to 140 kilohertz, which they never understood. Nobody understood that. I'll explain the transformer model to you. And 127.7 appears on the left side of it, so you are in the capacitive side. Then why are you complaining that your FETs are running hot and your coils are running hot, so on and so forth? That's one of the reasons AirPower failed. And 127.7 is you have your car fob. No, I have my car fob somewhere, this Nissan. It detects whether you are sitting inside or outside. That works at 125. So which genius set the frequency at 127.7? You're interfering with car electronics. So the Apple AirPower was jinxed from day one. I knew that. But if you tell them, they're so arrogant, they don't want to listen. They think I'm their enemy. I'm saying bad things about them. No, I'm trying to prevent you. Your best friends tell you on your face what you're doing wrong. The rest are smiling. They have a nice career. Okay, so this is what happened. Theoretical efficiency, as I'm saying, of all near-field methods is 100%. Don't get trapped into discussions of efficiency. This is the current in a resonant tank in a half bridge. You'll see there are two portions here. There is this portion, I've superimposed it for different loads. This is the part which goes to the output. This is through the diodes on the receiver side. This is the magnetization component. It is still controlled by the fixed voltage you have. You have set 5 volts or 12 volts. So there's V is equal to L di dt. It's controlling the ramp. So that is that portion. On top of that, this is riding. So this is the circulating component, and this is the one which is going to go through. And the receiver, as you see, every time it starts at 0 current. All the switches, all the diodes inside it turn on at 0 current. It's automatic 0 current switching. The only trouble is on the transmitter side, you need to ensure 0 voltage switching. That is the difficult part. Okay, so I'm trying to get forward here. So resonant circuits use leakage to their advantage. They use it to take out all the losses, say, in the parasitic capacitances of your FETs. You might have put EMI abatement capacitors on the switching nodes. It doesn't burn that up. It ensures soft switching. It moves all that energy into the supply rail. That's how you achieve such high efficiency in LLC, for example. And Qi and EV charging are going to land up in the wrong side. Qi has so many mistakes, I can't even begin to write a book on it. And they made it worse. If it was possible to make Qi worse, Apple did. You don't switch on the wrong side of a resonant curve. You never do. I mean, that's basic common sense. I'll show it to you. So I don't know which genius thought of that. Now, where did soft switching actually start? I don't know if you know that this was a controller I actually designed with it. And it has a fundamental flaw. I'll explain that to you. But this is the thing they tried for. It's a phase-controlled bridge. And they put a small leakage here. The purpose of the leakage was, when you turn off, during the dead time, it's going to push the current through the body diode, and then the FET switches. So the voltage across the FET is 0 when it switches, 0 voltage switching. That was the purpose of this. Okay, this never caught on for another reason. Microlinear had some of the greatest products, but they had fundamental flaws. They came up with the first PFC controller, if you don't know. They told me themselves. And they lost out to Unitrode because they made a fundamental mistake. I'll tell you that if you're interested. But anyway, now, if you add a resonant capacitor, I don't know if you can see this here. Yeah. And it is tuned to resonate over the entire cycle, not just over the dead time. You basically have 0 voltage resonant capacitor LLC. Now, just to tell you what happened, even if you don't have this resonant capacitor, you need a large blocking capacitor. If you use a half bridge or a full bridge, and you're running it in voltage mode control, little deficiencies or differences on either side cause staircase inductor saturation. It's well known. And the only way to avoid that is either put a blocking capacitor. It is all recommended in old Unitrode nodes, or use current mode control. So this was a flaw, and this is why the IC would never be reliable. But it was sold to Fairchild, then Fairchild sold it to onsemi, and they've recently obsoleted it, but they never changed this. They could never change the circuit diagram. This is wrong. You build it yourself and you'll see. It's staircases, or use current mode control. This didn't have current mode control. All right, so this is a practical Llc transformer. Okay, what is so special about the Llc, I'll tell you. This is the model which they typically use. There is a leakage, similar to the external leakage, but it could be part of the transformer. You make it very lossy. You put the primary and secondary far apart, so there is inherently a leakage. All right, so that is serving the purpose of this. And then there's a coupled portion. So this is deliberate. Now, the good thing is, you don't need any polyester, margin tapes, Litz wire, nothing. There's no proximity effects, nothing. This is the cheapest, easiest transformer to build, and if you build it, it's actually half the size of any flyback. It is the size of a forward converter transformer, but you don't have the output choke anymore. It gives you the smallest magnetics, and it'll give you 95% efficiency. But you should know how to operate it in the zero voltage switching. This is why resonant power is very exciting. However, there's a problem with resonant power is the frequency change. I told you, you can't keep a fixed frequency. Now, you can do frequency modulation. You can try to control the gain by changing the frequency. You'll get EMI, EMC issues. The first versions of Qi were doing that. They're going from 100 to 200 kilohertz. EMI testing starts at 150. Why would you go to 200 kilohertz? So that was, they didn't think that through. Then Apple came along and wanted to fix the frequency. The intention was good, but they fixed it on the wrong side of the resonant curve because they never understood that the resonant curve is not fixed at 100, it moves to 140, and I'll show you how. So, origin, this is how it goes. I'm just going from a standard topology and showing you. Less coupling. This is an LLC. You basically have introduced leakage. And you have got a resonant capacitor. And then the coils have changed, and this is wireless power transfer. But you don't have a optocoupler, because, so how are you going to communicate? They did something called backscatter. They have on the load, they have something which is toggling it, and the transmitter can decode that. So that's called backscatter. Okay, and that's where everybody gets very excited. Oh, this is the great thing. Oh, we are doing backscatter. And I say, stop. Let's not get started on that. Because what happens is, here you think you are in the heart of the complexity of a wireless power transfer or LLC system. This is the easiest part. Understanding resonance is the tricky part. And all the people in all companies are get engrossed in all these packets going up and down, and they miss the basic picture, which I'll show you. So you can come to that, but that's the icing on the cake. You haven't got the cake right, so what are you coming to here? So this is unfortunately the state of wireless power transfer today. So I told you I'll say it the way it is. Don't blame me for that, don't shoot the messenger. So I'm trying to warn you, and this slide is from a 2014 presentation I gave at IDT. I couldn't teach them, but they all got up and said, yeah, we understand what you're saying, but we don't know how to do it. I didn't have a solution to the problem. That solution was charge edge. It came many years later. All right, so I said, don't get mixed up. The devil is not in the details. It is, first get the bigger picture. Like scaling laws, it's a bigger picture. See the bigger picture, and then you know better. I could compare a lot of vendors and look at the current ripple ratio they use and said, oh, these guys don't know what they're doing. They have a current ripple ratio of 0.2, which means it's excess inductance, things like that. So, okay, I think we're stuck here. All right. So basically, wireless power transfer did one more stupid thing. This is the most stupid thing they did, okay? They introduced a secondary side capacitor, CS. Qi has it today. I'll explain the origin of that, and everybody is doing that. EV charging is doing that. Vitricity is doing that. Qualcomm is doing that. We don't have it. We have patented the removal of it. I'll tell you what problems it creates in a little while. Okay, so if I can get to the next one. All right, so I'm going to skip past this. C is very questionable. I'm going to come to that. Otherwise, I'll run out of time. Okay, so if you remove, they're very close. The topologies are very similar. You see, this is the same girl with the two faces. LLC is very similar to wireless power transfer. Okay, this was the idea of showing that. But the logic is different. So I'm trying to tell you, when I gave 2 seminars in IDT, one to ISSCC. I said, when you are starting on this path of wireless power transfer, please remember, you have to unlearn all what you learned in power conversion earlier. Your reflexes are just not right. You have to realize you are going in the wrong direction. This is an example. In classical PWM systems, you know that if you go to higher frequency, what happens to efficiency? It falls. Why? Switching losses. You know what happens in resonant systems? Okay. Nope. Does efficiency fall? No, it gets better. Because there are no switching losses. And that magnetization current ramp which I was showing you, if you have a higher frequency, the time for it to ramp up is less, so the peak to peak is less, the energy you have to recover is smaller. This is what happened at IDT. They messed around on the Samsung, I remember, told them, get 2% more efficiency, play around with this capacitor secondary side. They got it, and then they reported to the VPGM, we got the 2% by playing around with the capacitor. So they asked the senior director guy, so what do you think happened? He says, because of switching losses, I think what we did was we lowered the frequency. I said, gentlemen, go to the bench, please do your due diligence. All the data is there. The frequency actually increased. It was there, but they were just not looking at it because all the guys sitting in the offices don't come to the bench. I always am at the bench. That's where you learn power electronics. If you think you can sit in an office and learn it, no, good luck with that. So this is a real life story I just told you. The intuition is totally different. You have to cultivate a new intuition. And that is why the scaling laws and all I started looking at. My wife had gone to India, I was sitting with the dogs, and I was doing math cat simplest, and then I understood. I needed complete freedom from everything, and I deliberately trained myself to unshackle from conditioned thinking. So don't be conditioned reflexes here, okay? Now, next one. So as I said, these are the currents. I'm just repeating it once more here. Because this is what happened to the efficiency. As I said, if you go to a lower frequency, you give a longer time for the current to ramp up, and so your efficiency falls at a lower frequency. If you go to a higher frequency, that ramp up is smaller, and you get a better efficiency. This is what happened at IDT, but they didn't realize it. So they reached the wrong conclusion. I said, there are no switching losses. What are you talking about? Well, if you have implemented it correctly, there are no switching losses.
Excuse me, I don't understand what you say. Could you expand it a little bit better?
This one, this one?
No, the other one you say, well, it's lower frequency, why?
Okay, so this component, I told you the ramp is fixed. It is based on the output voltage clamping that coupled portion. V is equal to LDIT. The ramp you're not going to change. You fix the output voltage, it's a regulated system. If you have more time for it to ramp up, which is lower frequency, the peaks are more, the current RMS is more, and when you cycle it through your resistances, you generate I square R losses which are higher. This is what caused the 2% improvement in efficiency because they went to a higher frequency. They basically went from the green curve to the red curve. You can look at it that way. Yes, that is the main impact of efficiency. So that is what you have to reduce. And ensure zero voltage switching, which I'll come to. Okay, so yeah, you're right. So this is a loss visualization. This is again from my 2014-15 seminar. I tried my best to tell them what's going on. Losses on this side do not depend on frequency. You can show that it's zero current switching. It doesn't depend. It's just the shape of the curve. It's I square R loss, basically. On this side, it does depend on frequency, but it's the opposite dependence which you have in traditional power supplies. So higher frequency actually leads to better frequency. Now, you don't want to cross 150 because you're going to lead to EMI issues. I stay below 150, always. My system never exceeds 150. I track the resonant peak, but I don't introduce any additional frequency movement to modulate it. I'm doing a phase control bridge. So I track nature as far as it is, then I optimize my phase control. I'm not introducing any additional frequency movement. That will cause EMI issues and all that. And that is the reason people like to use the LLC, because it has a limited frequency range if you do it right, which he doesn't. They missed out the analogy between the LLC, and I'll tell you really, to be honest, I had learned the LLC before I went to IDT. So in Microsemi, my boss had encouraged me to do it, and that's when I did it. I wrote the book. And when I went, I realized it's the same thing. So in the interview, I'm trying to tell all the directors, you're doing the wrong thing. They went back to the VPGM and said, the guy doesn't know what he's talking about. We don't want to hire him. All of them, 3 of them said no. Luckily, the VPGM, Arman, knew me from Freescale days, and my boss, Bezad, knew me from Freescale. He said, no, the guy knows what he's doing. So they hired me. They kind of overruled all the senior directors. I'm telling you a true life story. So don't get put off if you don't get selected in an interview. It could be their fault too. All right, so This is just the efficiency data and all we recorded on a machine, and basically it's the same thing. You can have a look at it in your spare time. So the bottom line was, please unlearn 30 years of PWM thinking. If you say I come in with 30 years of experience in switching power supplies, it's all the more reason why I wouldn't like to hire you, because you don't have a fresh mind. Please keep that in mind. All the guys who come around, oh, I've been doing 30 years of, you can't talk to them. You can't explain any of this. He's listening to me because he's got an open mind. Many people don't have an open mind. Okay, so then I tried to, this was again, I presented at ID. The transformer model is extremely complicated. And even if you do simulations, the model they have for the transformer has limitations. Every package, Simplest or LT Spice, has a certain model which is not conducive to us, and I'll explain that to you. But anyway, I went through all the models, and I'll leave this for you to examine. I don't want to get into that. There are 3 types of cases, and simplest model, I'll tell you what you should do. Okay, this is a long paper by itself. Basically, the 2 coils don't share the same area. So the turns ratio is not equal to under root L1 by L2. So the whole model breaks down in very brief language. This is the simplest one you can use. Oops. Basically, this is what they are doing. They said, Chi, Vitricity, everybody said, tune the primary to 100 kilohertz, tune the receiver to 100 kilohertz. Oops, I keep pressing the wrong button. Sorry. They said tune this to 100, tune this to 100. When you reflect it, it becomes this. That's why I put it in red. This is a very bad circuit. This is not the LLC. LLC would be just this, no this. This has created a lot of problems. I'll show it to you. This is what their double resonator approach. They thought they're dealing with a radio frequency system where you have a radio, you tune it to 100 megahertz, and that's transmitting at 100, so you get the... It doesn't work like that. This is a coupled system. You have reflected impedances. Everything goes conky, all right? Very simply, I'll explain to you what happens, okay? And where you see the factor 4 by pi, it's coming from something called the first harmonic approximation. You'll find it in my book. Basically a square wave to the equivalent harmonic, so don't get puzzled with the factors. Just understand what I'm coming to here. So this is basically, a simplified model will explain everything to you what happens. This is the coupled portion, and this is the leakage. K is the coupling coefficient. All right. So if you have no load, the resonant frequency you will see is the series L and C. The entire primary inductance and the entire capacitance. I explained this to my lawyer at White & Case, and she started laughing. She, by the way, was an intern here at National Semi TI. So she was pretty, so we filed an Apple killer patent. When they realized that they'll never be able to recover. Seriously, she called it that. Okay, this is what happens. When there is unloaded, you will get 100 kilohertz. When it is loaded, assume that this is a very small load, 1 ohm. What do you think is the new resonant frequency? Think about it. It is basically the resonant frequency of this, the leakage and the capacitance. The coupled portion has gone out. So you have 2 extremes. One is the open load, no load, and one is the max load. And LLC moves between that. That is the advantage of LLC, so you don't have a wide spectrum of movement for the frequency. You can actually control it if you set the region correctly. I've shown that in my book, okay? That was the main advantage, attraction for LLC. But they also said LLC is not good for handling input variations. That's why they use it at power factor correction stages. I have shown you the process in my book, and I actually built it to do a 4:1 variation at the input. It's very easy. Okay, so now you understand what happened to the transformer model, and I'll show you the actual plot next, I think. This is what happens. So no load, you have 100 kilohertz. As you start loading it, it slickers, and then at maximum load, it bottoms out at the frequency where the leakage is resonating with the primary capacitor. And that's it. This is one peak, and it moves between 2 extremes. The problem with so it's an LLC. You get 2 peaks, it's 1 peak, but moving. The moment you introduce the secondary side capacitor, it's an LLC-CR circuit. Now you have multiple peaks, both moving in contradiction. You have no way of knowing what the gain profile is. This is what the problem everybody is facing, I just told you in one simple sentence. The moment you see the CS, they don't know what they're doing. We have patented the removal of CS because that creates another frequency. I'll show you exactly what happens. So do you understand this? And this point you're seeing, all the curves are uniting. Can you see that? There is one point where they all unite. So all the load curves, if I set the frequency here, almost exactly at this point, I will be able to meet any The demand is this. Basically, it's a gain profile. This is your output voltage. I'll be able to maintain an output voltage without changing the frequency for any load. Look at it very carefully. It's very similar to what we have in continuous conduction mode converters, where you have a duty cycle, it doesn't depend on load. You can get 1 ampere out of it, you can get 2 amperes out of it. Duty cycle doesn't change. It's automatic regulation. This also is automatic load regulation. So if I operate at this point, I will get automatic load regulation. The problem is LLC is easy because it has a fixed coupling. A wireless power transfer, every time you put your phone on it, it's a different coupling. Now you have to adapt to that. How are you going to do that? That is charge edge. That's exactly what I'm doing. I put my coil like this, I put my coil far away, it'll adapt. It knows where the peak is now. Within accuracy of 200 hertz, actually, if you want to know. So, this is the magic operating point, which I've been telling them you should use it. LLC uses it. In my book, I have described how to use this point. But, as I said, LLC is fixed coupling. Wireless power transfer is variable coupling. And you can't screw up matters further by introducing a secondary side capacitor. You have no idea anymore what's going on. Okay, so I'm going to go fast now. So this is what I did in scaling laws, because that's the original topic. Basically, I chose a kernel, which was 159 hertz. I analyzed it. I just chose random components with a certain coupling. 10 microfarads, 100 millihenries. I didn't care. I had a leakage, I had this, and I modeled it. And then I said, okay, so now I know exactly that I should operate around this point. This is my best operating point. A gain of almost 1.05 actually. And you should have a curve which goes slightly above that so you don't roll over. So that's all given in the book. Once I got it that it works till 300 ohms, I know the power I get from this system. And then I said, okay, so now I've understood that. By the way, the series resonance circuit, I just gave you one slide here. It doesn't work because for that you have to change the frequency from 0 to infinity. That's why no series resonant didn't catch on. LLC is popular for that reason. But let me move on to the next slide. Then I said, okay, so the frequency, so I know what the frequency scaling factor is if I want to go from 100 kilohertz to 50 hertz, and I apply that scaling factor and I get my same power, I get higher frequency, 100 kilohertz. Then I went to the next slide and I said, okay, but my power with 300 ohms was just 5 watts or 10 watts. Now I want 20 kilowatts maybe. What do I do? So I went back. I applied the power scaling factor. You see what I'm doing here? Oops. L I'm dividing by the power scaling factor. I told you if you double it, you have to halve the inductance. This is what I'm using here. And capacitor, I'm multiplying. This is a trick. As I said, my LLC design topology is 5 lines. I can design it for any power. One guy wrote to me saying, you showed me how to design a 20-watt converter. You didn't show me how to design 200-watt converter. I said, yeah, all you have to do is to divide the L by 10 and increase the capacitance by 10 and you'll get it. So it's a very simple thing now. So this is the importance of scaling laws. Any questions? I know this is complicated, but think the whole world got this wrong. So you can't be blamed for not getting it in 1 hour, but the seminar will be available for you. I'm very happy to share it with you, and they can upload it, do whatever they like with it. This is a Fredley's article. I compared everything with this, and I found it matches it exactly. But this is a huge article with 20, 30 curves to design it, and mine is 4 lines. So there's another book, Marian Kasparek. He's written a book on resonant power. My boss used to love this book. And by the way, there's a master's thesis, which is on the web, which justifies part of what I did. So everything I don't reveal, but my phase control topology, if you search for Marian Kasparek, Wright University, Charjit, Sanjaya, you'll find this thesis. Not everything is given, but you'll realize something very interesting here. So he loved this project. Marian was taken out of his mind when I did this as a post-justification. After we had all implemented it, a student, an Indian girl came and said, I'm trying to do my master's. I said, okay, why don't you take this up? It'll help me also. And she did it, and Marian Kasparek loved this, so she got it right away. Basically, the important thing is that if you're doing frequency modulation, you run out of efficiency very quickly at light loads. With the technique we are doing, which is phase modulation, you can maintain flat efficiency all the way to light loads. It's verified in this thesis, okay? But that's not all. We also track the frequency. So the EV charging guys are doing phase control today, but they're doing it at a fixed frequency. We are doing phase control too, but intelligent phase control. We actually monitor where the peak is and settle to the best point. That they don't know how to do. Okay, so Basically, there's a gain profile, and you have to be clear where you are, and that determines the power you're getting. So I'm not going to get too deep into that. But I tried to show this at IDT. So if you have set a wrong gain target, suppose your gain target has been set wrongly here, now to go from no load to max load, you have to span this entire frequency range. You see, this is the point where all the curves meet. I told you that. This is the magic point. So I said, no, so Qi doesn't get it right. They have this wide frequency of operation, and then they don't allow it to go beyond 200 kilohertz. And at 200 kilohertz, if you still need to reduce the power, how did they do it? They apply Zener clamps on the phone, inside the phone. That's going to kill your battery. I had an Apple Watch, my wife uses it, which got hot and exploded because of that. That is the Zener clamp issue and the receiver coil heat issue. Two things are there. Okay, so I said, why don't you do this? Change the gain target. You see now the frequency variation is smaller and smaller, and if you reach the magic operating point, you will have, but of course this is for a fixed coupling. Now the trick is how do you do it for any coupling, and that's our firmware. So this I tried to explain in 2014 and 15 to them. So that was my experience with LLC coming to play in wireless power. So importance of so you can basically decide to change the frequency modulation, you can do phase control, you can do duty cycle control, you can try all the tricks, by the way. And you need an optimum profile, but I'll tell you what better thing is to do, Qi. When I entered IDT, this is the curve they always had. This comes from Fulton Innovation, E-coupled. Do you know how Qi developed? Qi was in Amway. It was a water purifier project, a Skunksworks project. Their own company, Fulton, because they are on Fulton Street, that's a subsidiary of Amway, created the first standard. Okay, that panned out into the WPC standard, the Qi standard. The first version was Amway. Amway still owns most of the patent portfolio, but you don't know that. Anyway, this is the curve they always showed you, simple curve. Oh, you want more high power? Please lower your frequency. They assumed that this is 100 kilohertz, this is about 105, you don't want to hit the peak, and then you don't want to go beyond 200. This is how Qi was supposed to work. It's a wrong curve. Qi doesn't look at all like this. First of all, even if you don't have a secondary side capacitor, the peak shifts to 140. I told you, the peak shifts to under root 1 minus k, which is the leftover, the leakage. If you do it for 50%, you get 1.414. 100 changes to a 141, exact figure. Do the resonant frequency calculation I showed you. Okay, so what really happened was, so they started going like this. The actual peak shifted, as I told you, and they rolled over, and kaboom, transmitter says, oh, now the power is decreasing, it switched off. And they said, this is the poor user experience of inductive systems. Wrong. What more resonant are you going to make it? You thought you tuned the receiver to 100 kilohertz, you thought you tuned the transmitter to 100 kilohertz. What is more resonant than that? Actually, you had the wrong resonant frequency. That was the problem. Because you're not supposed to have a secondary side resonance, and the primary side moves. And even this curve is not a smooth curve. With a secondary side capacitor, it has got two humps, I'll show you. So this is how Qi started, all right? And it still has that. They are stubbornly not telling you what the truth is, but this is what we corrected. The important thing is I'm not coming as a critic. I have corrected all this since 2 years. Okay, so everything I'm telling you, this was a double resonator myth. And this is the original patent. It is still assigned to Amway. David Barman, he's a well-known guy. You'll see him on LinkedIn. They said tune both to 100 kilohertz. This is exactly how it started. This is a 2019 patent from Qualcomm Halo. Halo was a company in Auckland, University of Auckland. Do you know that? Qualcomm bought them. It's the same patent portfolio which is shared by Power by Proxy, which Apple bought. Same guys exactly. Okay, I don't know how they divided the patents, but it's the same guys. They didn't get it right in Power by Proxy, they didn't get it right here. They have exactly the same mistake here. So, Vitricity has the same, they have a white paper which says tune both to the same frequency. I'm not getting this. So this was the story of Vitricity, I just moved past it, but everybody had this false double resonator approach, and I'll show you what the problem with that is. Okay, so you know Halo, Qualcomm sold its entire patent portfolio to Halo, to Vitricity in early 2019 for EV charging. Okay, so double resonator myth. This is the Vitricity white paper. Look at the frequency they're giving you. This is not the model. I just showed you the model. There's a leakage and there's a split portion. They think it's a simple LCR circuit which you learned in high school. It's not that. Okay, so then you come up with a wrong premise and you never correct it for 10 years and you land up in 3 kilowatts in a BMW. And Rezence failed. Vitricity was responsible for that too. They got a, Mojo Mobility is somewhere in the Bay Area and they got a big DOE grant and they have the same thing. Whenever I see a secondary capacitor, I know they're on the wrong path. I'll show you what happens with that. So tuning board, this is a patent portfolio of Hello. Now I ran a MathCAD spreadsheet and I can switch in and out. This is the actual MathCAD spreadsheet. Leakage, LMAG, I can switch these in and out. There's a secondary side leakage, I can switch it in and out. There's a secondary side capacitor, I just put 1 or 0 and it switches out. I'll show you the results. The MathCAD is here and there's a video. You can slow down the video, you'll see all the lines of the MathCAD. I haven't hidden that from you. Okay, I'm going to scroll through this, you'll see it's going to, all the lines are there. I've not kept this secret. This is basic physics. I can't patent this. This is basic physics. Okay, so I'm showing you the curves, how I generated them. I've done that in IDT also. Everybody agreed with my curves, so it's not like it's not been peer reviewed. Everybody looked at it and said, yes, this is correct. So nobody at IDT said I was on the wrong path. They just didn't know what to do with this burdensome knowledge, basically, to tell Chi that they are wrong. I mean, nobody wants to do that. That was the main problem. So, okay, then I can switch the capacitor in and out. This is this MathCAD spreadsheet. And if you want, just write to me and I'll share it with you. There's no problem. You know my Yahoo email address. I've sent it to quite a few people. A lot of people write to me and I send it to them. So don't worry about that. Sharing is also very important. So and tell me if there's a fault in it. I don't see any fault in this, okay? More important, I want you to tell me if I went wrong. Okay, so this is the video. And now I'll go to the next slide and show you the results of that. This is a pure LLC with no secondary side capacitor, no secondary side leakage. Look at how the curves are, exactly what I showed you. It's tilting to the side. I'm doing that in slow motion animation. Higher load, lower load, more load, more load. It bottoms up between two values. I told you it's for a coupling of 0.5, about 140 kilohertz. Okay, so this is pure LLC. Now just see what happens on the next one. Now, I've given you the values here. Now I have introduced the secondary side capacitor, which Chi has, which Vitricity has, which everybody has. See what has happened to the gain curve. Now you have two peaks, as I told you, and one peak is moving to the left, actually. One peak is going to the left, one is to the right. There are two LLC, it's a LLCCR now. Okay, so, and then I'll superimpose and I'll show you what happened. Now, this curve which I just got, I superimposed it here. This is the curve, right? IDT has a white paper and app note where they have given, I've given you the details. They're saying this is a good coil design and this is an improper coil design. First of all, I said this does not happen. When you use a CS, you have to have the right transformer model, which I just used, and that gives you this. And if you are saying this is the improper coil design, this is exactly what happens when you have CS. See, look at the curves. You have this peak here, and they have not plotted on a log versus log scale, so it's looking a little different. It's exactly the same curve. This is the curve you get from basic physics if you introduce a secondary side capacitor. And they have it in Chi, and they have it in Vitricity, and everybody has it. We are the only people, and we have patented the removal of CS, I told you. That was my lawyer's idea. So now I've just taken their thing and added a leakage on the secondary side, and I'll compare all of them. So now this is what happened. This was my pure LLC. So if I removed my secondary side capacitor, assume there was no leakage, this is the curve, and this I can handle. At least it's a little predictable. I know that I can change the gain profile when I go like this. The dotted portion is where you get capacitive portion. It is not conducive to zero voltage switching. So I have broken this into two. This is what they get if they introduce CS. You see this? And if you introduce on this, you introduce the secondary side leakage, which is actually realistic. Now you have real weird portions. You can't even get the right gain. The gain has dropped, and you go into capacitive regions in the middle of it, and you get that control inversion too. But you get multiple control inversions, which when I gave that presentation, I said it's not like this. My senior firmware guy said, oh, now I understand. We have been calling this control inversion. That means we are reducing the frequency, and the voltage, instead of rising, is falling. They had observed all this. But they didn't know why it was caused. So this is what's happening. Now you understand the CS is a big problem because it's creating multiple resonances. And the frequency peak is shifting. Nobody understood that too. This is a composite. Now, that was for a fixed coupling. If I change coupling, what happens? This was another curve I presented in 2015. Now I've changed coupling and load. Now, fixed frequency methods, I'm going to show you what happens to them. So I'm going to run this. It's a simple, I'm taking a simple schematic. I can share that with you. And I've distributed, there's no CS. So I'm keeping a simple LLC circuit. And I'm going to try and show you what happens with fixed frequency. It gets worse with CS, but even without CS, it's bad enough. So I'm switching at 5% higher than the resonant frequency. I'm going to focus on something called the transistor current. So you see this transistor current is nicely well behaved. And just before I put a sensor there, probe there. And just before it turns on, which is this red thing, it is slightly negative. You know what a negative current means? It's going backwards. Where is it going? It's going into the diode. You see that diode? It's got current in it. And you see the switching node has gone high. So when you switched finally, when the thing went up, the switching node was already high, which meant the voltage across the FET was zero. You just got zero voltage switching here. You can see this video later in your spare time. Okay. When you switched, you see the switching node was already high. When the upper switching node is high, that means the voltage across that FET is zero. So this is the correct way. So you operate to the right of the curve, everything is fine. But you should know what is the right of the curve. If you don't know where the resonant peak is, you don't know where's the right and where's the left. So this is what happened to Apple. So now I'll do it with the wrong side. I'll go 5% below the resonant frequency and show you what happens. Exact same schematic. I'll confirm I just set the frequencies to 106 kilohertz. The resonant frequency in this case was about 110. So I've set it all at about 106. And I'm going to run it and show you what happens. 5 minutes. All right, so what happens here is, I'm again going to focus on the current. This is the transistor current. It's gone to 200 amperes. And if you look at it, it's happening exactly during the crossover. So there is no zero voltage switching. So the entire video, during this time, this current through the diode is not there. So this current is 100, I put it in log scale, 200 amperes, and the switching node is still low. Then the switching node went high and you got that spike of 160 amperes. You have a huge crossover loss. Your efficiency will come down 10 or 20% because of this. Okay, so we are running short of time. They didn't realize the location of the peak. They introduced CS, they introduced fixed frequency switching. They lose the EVS. It interferes with your car frequency. Everybody made the mistake, and if you look at the WPC calls, even the frequencies they didn't understand. It's 72 to 122, even they couldn't tune it to 100 kilohertz. They didn't understand the ratio of C by L from scaling laws. The receivers are all over the place. So then they have an interoperability issue. Today, the reported interoperability has fallen. The failure rate has gone up to 61%. See the links. That means there's a 1 out of 3 chance that your phone will work on a transmitter. That's their own lab data coming out. So that's about it. I'm going to start ending it here. And this is how we do it. You saw the flux laser principle, and we have a very smart firmware, and I finished in time. Thank you. Sorry. Any questions, please?
Yeah, a few minutes for questions, maybe about 5 minutes, and then we'll wrap up. We have to be out of the room by about 8.
What's the time right now? We got time. Yeah, I'm free to talk to them, yeah. Yeah, that's fine. So we can even continue the conversation outside. So did you understand, is there any questions? Don't feel stupid to ask, this is resonant power. If nobody understood it, don't feel embarrassed asking a question. The only way I got it right is I asked questions to myself, read books, read Lee's books, everything. I said, no, this is not making sense. So please question yourself, yes.
Well, like you, I like to ask a lot of questions, and I like to ask real fundamental ones. So a fundamental one is, so if this is so simple, and everyone else was wrong, could figure this out, and some time ago you laid it all out for all these people, Why aren't they using your IP and everything
Well,
ubiquitously?
a lot of people
why-
are
why-
paying very close attention. So that's a good question,
Right.
but we are
Yeah.
not into PR and getting investments. I stayed in the lab buried there till I got the firmware right. My style is different. We did make any PR material. We are putting out a little videos, but we are not revealing everything that we are doing. And so people have now, it's so difficult. You know, I have to stand in front of a very technical audience and explain it to them. The average person won't understand this. So that's, and also the myth they have created of what they are. Can you tell me that I go to them and say everybody else is wrong and I got it right? Yeah, I have the results to prove it, but I have to be there to show them the results, right? So it takes a little hard sell when you are inundated with so much of misinformation.
All right, thank you.
Let me just stand up. So you mentioned that the Qi topology is wrong, so that when you run this, in your case, the frequency below the resonant frequency, you see hard switching, right? That's basically what you say, because it's a hard switching causing the loss, right?
Yeah.
And I happen to have a chance to run these kind of systems, and we don't often see hard switching. And every time we see hard switching, we know we have a loss. And we try to figure out a way to compensate for it. And I just don't, in my experience, I just don't see, based on the Qi system, I don't see a lot of hard switching situation happening.
You don't see hard switching in a system. That's how I told you we improved the efficiency by 2 or 3%. Qi efficiency is still very low. Considering it's a well-coupled system,
Yeah.
it is still very low, 70%. When IDT publishes something that they are getting 85%, please look very carefully. They are not generating 5 volts, they're generating 12 volts or 18 volts. Just see all the tricks they play. So when you have a high current, first of all, there's a receiver side loss. If you increase the voltage, your receiver side current is lower. So the resistance of the receiver coil goes a little out of the picture. So I can tell you, you can do all the simulations. I just did that to you. It is real. Now, how real it is, it's either you believe it or you don't believe it. There is physics behind it.
I think what you see makes some sense, but I just don't have the experience to see it. The other fundamental question for you, I just don't understand. Kind of stupid question from me. So is, where is the major loss? When you do this, let's see, it's a loose coupling. Coupling factor, let's see, only 0.40% coupling. Normally, right, that's the case, right? 50% coupling. And where's the major loss?
Yeah, I told you, receiver side loss. If it is 70% to overall efficiency, 20% is in the receiver, because the resistance of a typical Qi receiver coil is about 400 milliohms to 1 ohm, whereas the transmitter is about 20 or 30 milliohms because it's a thicker coil.
Actually, that's not what we think. What I think, at least, I think it's just when you do this kind of thing, you have.
So if you have worked in Qi, it takes a little while to realize you have been on the wrong path, and I'll give it to you. If you have worked on it, I know that at IDT, all they did was trial and error. Nobody did a system level simulation till I showed up or after I left. So they would put it they would do device level. So I see, oh, the transistor is turning on, the charge pump is turning on. But to do a full sweep, you also need to combine it with MathCAD. I only do that. I do MathCAD, then I simulate. So I know what I'm looking for. All my books have been written that way. I first create MathCAD files because then that teaches you the equations. Then you do sanity checks with simulation. I've never run a simulation, just you'll get wrong data. Okay, go ahead. Anything?
All right. Well, thanks I think that's all the time we have for questions. I'd like to thank our speaker, and let's give one final round of applause. I have a certificate of appreciation for you.
Oh, thank you. Thank you so much, Michael.